we're going to let that stand. The graph of the function is concave up on an interval if the first derivative is increasing. If the first derivative is increasing, the first derivative increasing means that it is concave up. If the first derivative is increasing, don't worry too much about that. We don't emphasize that portion of it to that extent, but this is the way our book's explaining it. So if I take the second derivative, I'm taking the derivative of the first derivative, and if I have all of my if my first derivative is increasing on an interval, well, this is interesting. I'm going to put this in red. It's more than I was thinking about. Let's consider, what's the first derivative right here? 0. What's it right here? Just take a guess. -1? Okay, it's negative, right? Which is greater, 0 or -1? 0, right? Now, if I come up here and I have a steeper tangent line, which is greater slope, absolute value-wise, or let's say it this way, which is the greater slope? Forget the absolute value part. Which is a greater slope? From this tangent or this tangent? Which one? Let's say the first one or the second one? Second one. Because you know on a number line, you know, this value, if this is 0, this value is less than this value, but this could be -100, and this could be -50. Which one is greater? I said it wrong, didn't I? Let's try that again. Which one's greater? -50 is greater. So what this is saying is that the first derivative is increasing on the interval. So if I take a look at the derivative here, and I take a look at the derivative here, is the slope increasing as I go from here to here? Now you have to think about this. If this has a slope of -100 and this has a slope of -50, which one has the greater slope? The second one. Okay. Are the slopes increasing in value as we go around the curve? They are. Okay. That's where those negatives can kind of throw us. And then as we continue on, I don't think there's any question as we continue on that our slopes keep getting more and more positive. But it's over here in the negative. We have to think about it. So is it true that when it's concave up, the slopes are increasing on the interval? Yeah. They could be negative. Doesn't say that the slopes are positive, but they could be negative. Okay. If it's downward, if it's concave down, then the slopes keep getting lesser and lesser. And so over here, you've got a slope of 0. And here you've got a positive slope, right? 0's decreasing. That means it's a net less than. And if I get over here, I've got a negative. And so the same thing happens, that we are decreasing in value of the slope as we go around this curve. Now, what happens at the inflection point? If I'm decreasing in value as I come around this curve, but I'm increasing in value as I come around this curve, give me another explanation for the inflection point. I'm decreasing the slope value as I come around this curve, but I'm increasing as I come around this curve. So my slopes are, how can I say, the direction of my slopes are changing direction. I'm decreasing in value on slopes, and then I begin to increase in value on slopes. Okay, well, let's go on. That was kind of a new thought. I hadn't really thought about it in that way, but it's absolutely true. Test for concavity. Let's see what we've got here. The function whose second derivative exists, okay. The second derivative is positive. The function is concave up. Have we said this before? Second derivative is positive. The curve is concave up. Kind of a repetition of what we've just been talking about. Second derivative is negative. The slope is concave down. Second derivative positive, concave up. Second derivative negative, concave down. Coffee cup up, coffee cup down. Positive, second derivative values, it's positive that we have our coffee staying in our coffee cup. Okay. Guidelines for using this then. It says first locate. We're not doing time anymore. Okay, thank you. We're not doing time. But I need to hide that from everyone so no one can see it anymore. The new program doesn't make me have to do that. I can just keep talking forever now. Okay, locate the input values for which the second derivative is 0 or the second derivative is undefined. So we have to first take the second derivative now. That's going to be the main thing. And then find out where the second derivative is 0 or undefined. And that or undefined is really important. Use the input values to determine the test intervals. What are we talking about when we talk about test intervals? Did you do any of this in section 3.2? Did you find some critical numbers and then set up some intervals and then take some test values? What was that? What was that whole thing we created? Sign chart, yeah, a sign chart. So in other words, set up a sign chart. So we're going to go through an example of this and make sure that we know how to deal with this. Okay. Analytically, determine the open intervals on which the graph of this function is concave up and concave down. Step number 1. Back here it said, locate the inputs values at which the second derivative is 0 or undefined. I can't do second derivative until I do what? Okay, so let's determine the first derivative. That's all. Just take the first derivative. Now, look at that. Taking the first derivative, in chapter 2, we were developing all these rules for how to take derivatives. That's basically it. The rules for, the way to take a derivative of product and a quotient and a composite function and some implicit differentiation and all that stuff. We worked hard to know how to do that. Now, we take a look at this, and all we have to do is take the derivative. That's all. But we have to remember chapter 2. This is why it's also cumulative. There's no way I can test you without testing you for the whole year's worth of information. So, tell me, which rules do we need to use for this derivative? We're going to take the chain rule of this part, but what else? The product rule. Okay? So we're going to take the product rule and then the chain rule. So the first derivative is, give you a little practice here. So there would be our derivative showing the line of intent, all the derivatives we intend to take. So let me go back and I'm going to stop this because only 7 of you had a response. I'll ask you another question instead. I'll have a question for you, so don't worry about it. I have a derivative. Now, it says to determine the open intervals in which the graph is concave up and concave down. We're going to do one more thing. Okay, I want to know, are there any extrema? So we're just going to throw that in here also. If I want to know if there are any extrema, what's the next thing I have to do? Yeah, I'm going to have to determine my critical numbers. Now, these are critical numbers of the function. Okay, and I do that by setting the first derivative equal to 0 or determine where it's undefined. And we can't ignore that piece of it. So let's see. If I want the first derivative, if I look at this, I'm going to do a little bit of work on this first. If I'm going to determine where this first derivative is 0, there's some stuff I need to take care of first. Garrett, what do you think? Well, I'm going to get to that, but before I do, let's help me with this. I mean, if I want to set this equal to 0, it's going to be a little hard just to take this and set it equal to 0. I'm trying to come up with something that's okay. If I factor out an x minus 4 squared, I'm left with okay. So in other words, I would have down here, I'll just do a little piece down here, and this is going to be 4x minus 4. Why is that important to put it in that format? What's so significant about rewriting this as a product as opposed to a sum? Yeah, and this is something you did, I know you did back in Algebra 1, okay? You know, in fact, you did this back in elementary school. If you have two numbers that multiply to be 0, you only got that if one of the numbers was 0 itself. So that whole basic computation Algebra 1 idea is what we're going to be using here. So our critical numbers, x equals 4, x equals 1. Okay. Let's see. So I've taken the first derivative, and I want to find the intervals of concave up and concave down. So I best get on to doing what? Second derivative. Determine the second derivative. The second derivative is the derivative of the first derivative. We're just going to continue this pattern here. When you look at the first derivative, are you going to take, this piece? Are you going to take this piece? Are you going to, you decide which form of the first derivative you want to take. I think I'm going to take this form of it. But now that I've chosen this form of it, by the way, I just factored a 4 out where the 4 came from. Okay, factor the 4 out. I'm going to have to use the product rule and the chain rule again to find the second derivative. Okay. There's my second derivative. Determine what? Determine what? Let's go back. We're trying to find what part? What are we trying to do? Okay, where's concave up, where's concave down? And change of concavity is where the second derivative is 0. Okay? So, and when we find that, we think, we're not sure though, Garrett, so don't assume that they're inflection points. Sometimes they're not. So we're just going to say we're going to find critical numbers. Now, critical numbers of what correspond to zeros of the second derivative? Critical numbers of what other function? f of x or the derivative of x? F of x.